Okay, the region that we want to define then is the region defined by theta from 0 to pi, r from 0 to sine theta, just this region in the xy plane. But now we want our z to go from 0 to 1 minus r squared. And you could confirm that that's going to give, that region is going to be the upper half of a sphere. Okay, now to describe that region in all three coordinates, theta, r, and z, or to deal with that region, to answer questions within that region. In the first question we're going to answer is what's the mass in that region if you're given a certain density function. We need an increment in terms of r, theta, and z, a delta r by delta theta by delta z increment. So a delta r, delta theta, delta z increment gives us a little box here. Okay, the base of that box is just our delta r by delta theta interval, which is going to have area r star delta r times delta theta, the same as the interval directly below the box. The box is then going to have an altitude, which is delta z. So the dimensions of that box are going to be, well, it's delta r by r star delta theta by delta z. That's something like a cube. It's not really a cube, it's close to a rectangular parallelepiped, but I wrote cube with quotes around it to kind of invoke that idea. So it's a little box. Maybe I should have just written a box with a volume, delta v equals area of the base, r star delta theta times delta r times its altitude, delta z. Now, if the density of whatever fills this region is given by rho of, it almost looks like a P, but I didn't put a tail on it, I don't know where that came from. Okay. It's a rho of r theta z, and it could be any function. In this case I chose the function 1 plus rz tangent theta. Now that wasn't a real good choice because of course the tangent of theta blows up as theta approaches pi over 2, so it's not a particularly realistic density function, but we can still talk about it, okay? Not very realistic, but it's just a function. So what is the mass corresponding to our volume increment? Our volume increment, r star delta theta, delta r, delta z. And let's make sure we understand that this volume increment, our typical volume increment, contains the point r star, theta star, z star. Okay, so what is the mass of this increment? Here's its volume. Here's its typical point. Well, we evaluate the density at our typical point just as we have with densities in the plane. And we multiply that by our volume increment because density times volume is going to give us mass. So our mass contribution is going to be this. Here's our density using r star, z star, and theta star instead of r, z, and theta, because now we're being specific to some region, multiplied by our volume increment. Okay, area r star delta theta delta r, altitude delta z. Okay, well then that gives us total mass of what? We have our description of the region. We have what happens in a typical subregion. If we use the usual process, summation and so forth, and ask all the important questions, we can confirm that this leads to the integral where theta goes from 0 to pi. That's a fixed set of limits, okay? And for every theta, r goes from 0 to sine theta. And for every r, z goes from 0 to 1 minus r squared. So we're going to have the integral of, I didn't have room to write it, but I wrote it down here, 1 plus rz tangent theta from this term, times our r from here, our delta theta from here, our delta r from here, and our d theta from our delta theta, dr from our delta r, and dz from our delta z. This integral will work. We start by integrating with respect to z. So that's going to be our innermost integral here. And then our z's are going to go away when we substitute 0 and 1 minus r squared for all of our z's. Now the next integral is not going to have any z's in it, but it's going to have r's. It's going to have r from this, and it's going to have r's from substituting 1 minus r squared in for our z's. And then we integrate with respect to r. Okay, we don't have any z's left, but we have r's. But now we're going to substitute 0 and sine theta for every r, so that all our r coordinates are going, or all our r's are going to go away, but we're going to still have thetas, both from the tangent of theta and from substituting for the sine of theta. So now we have an expression only in terms of theta, and I could have put a couple of parentheses, okay. Everything in this blue parentheses is going to be a function of theta, which we can integrate with respect to theta, assuming it's integrable. Assuming we calculate the integral, which might be a little challenging, especially since we know we have a infinite limit as theta approaches pi over 2. But in any case, we're going to get a theta increment here, or a theta function out of this, which we integrate from 0 to pi with respect to theta, and that's going to be the mass of this region. Now we can also do moment integrals, moment of inertia integrals. And it's equally easy if you know the rules for moment and moment of inertia. And hopefully then from physics you understand the meanings of moment and moment of inertia so that it all makes sense to you.